right, so after our last question, the dreaded particle motion, actually, hopefully that's not all that hard. Just we go ahead and mix a little bit of technology into that to ease the burden of some of the crunching of numbers. So let's see what we got. So we have our story is that we have some particles moving along according to this little equation. So I guess I'm just going to go ahead and take a second to set myself up with this equation, 3/4 x cubed, 10x squared. Looks like we got a 21x and a 36, so that we will just have that down the line. It looks like what we have is an instantaneous velocity is my first question, which of course we should know that the instantaneous velocity, which is v of t, also known as s prime of t, is 9/4 of a t squared with a 20t and a 21. Of course, our derivative of 36 is 0, so we're good to go. Now, the acceleration, which would be s double prime of t, also known as v prime of t, also known as a of t, all of these things are synonymous. Takes a while to write all that down, would be 9/2 t minus 20. All of these things would be a of t. Not a particularly complicated set of information. So what I want to know is what is the instantaneous velocity at 10? So I would like to know v of 10. Now, of course, I could certainly plug in the number 10 in all of these locations, and it's probably faster to do that than what I'm going to do, but I'm going to go ahead and plug this thing in, my actual velocity equation, because I think I'm going to use it in a couple of places. And so there's my velocity equation, which was y2. So what I'm going to do is I'm going to do my y bars, but instead of doing y2, I'm going to do function y2. Okay. And I'm going to ask my calculator to go do that grinding stuff and say, oh, okay, sweet. y2 of 10 is 46. So I got 46. And again, if you look very carefully, it talks about this thing moving along a line in meters and in seconds. So the velocity is 46 meters per second at 10. Now, of course, if we wanted to find the acceleration, we could do the same thing. This one, I do not think it's going to be worthwhile for me to take the time to plug that in because that's a relatively simple number of, let's say, 45 minus 20, which is going to be 25. And this is one is going to be meters per second squared. So keep in mind, position was meters, velocity is meters per second. Every time you go down a level, you end up adding another piece of that variable in the bottom. So this is meters per second squared. So now it actually starts asking some more significant questions about what is actually happening to the particle. So what I think I'm going to do is right down here, I'm going to make myself a little graphical organizer talking about v of t here and a of t here, because the idea of at rest, speeding up, slowing down, all of those things are definitely linked together. So what I think I'm going to do is start by talking about this part right here. When is it at rest? So let's go to that program quad, because we do have a quadratic in this problem where A was 9/4, B was -20, and C was 21. And so according to this, I found that the particle was at rest at 1.216 seconds and at 7.672 seconds. Those are the two locations when the particle seemed to be at rest. So we could write that right here. T equals 1.216. T1, T2 is 7.672 seconds. Now, notice it didn't ask me where the particle was, but I could find that out if I wanted to. Now, I know that this is the velocity. This is a positive parabola, and all positive parabolas are up on the sides. And of course, down in the middle. So I know that this particle is moving forward, moving backwards, moving forwards. Going a little bit further, I could look at my acceleration function right here, which was 9/2 t minus 20. So what I might want to do is take that 9/2 t minus 20 and figure out when that value would be 0. So of course, if I move that 20 to the other side and divide by 4.5, that happens to be at 4.444. And honestly, since we're using all decimals in here, I'm not going to bother to do something more fancy. And again, this is a line that has a positive slope and a negative y-intercept. So it started out below the axis. And of course, since it has a positive slope, it's going to end above the axis. So when it comes to these questions about speeding up and slowing down, I know that this thing is going to be speeding up anywhere where the sign of both are the same. So this would be a region where it would be speeding up is in here and in here. And anywhere where those two things have the opposite signs would be slowing down. So that would be in these two regions here and here. Now, of course, this problem is not thorough. There's one little piece that is missing, and that's sort of the assumption that it started at time 0, which is what we would usually do. So just moving along this thing, I would say that it was slowing down from 0 up until 1.216. It was also slowing down from 4.444 until 7.672. Now you'll notice that I did an open bracket at that because it actually hadn't stopped at that value, whereas it did stop. It did stop accelerating. It did stop moving forward. So I kind of took those out of the puzzle, and my speed up regions were from 1.216 until 4.444. And it also sped up from, let's see, 7.672. Actually until infinity, because this particular problem never told me to stop anywhere. Now, the last two problems aren't going to be too bad, but we need to find the total displacement of this thing. So what we're going to do is find what happened. Again, displacement talks about my original function, y1. So I'm going to say vars, y vars. Let's find out what happened at 12 seconds minus vars, y vars, what happened at 0 seconds. In other words, where did it end at 12? Where was it starting? Take the difference of those two values, and I got 108, again, meters. So I'm going to just say S of 12 minus S of 0 equals 108. Of course, if we wanted to, we could be a little bit more thorough and actually specify that this was at 144, that this one was, let's see, at 36, and show where each of these values was coming from, leading to that answer of 108, but it's all good. Now, here's the last problem. And again, this is the one that's giving people a little bit more grief. And that is when you're looking for the total distance traveled over that 12-second period of time. I know that the particle was going forward from 0 until 1.216. So I'm going to find the displacement from 1.216 as it was from 0. This little piece would be how far forward it went in that first region. Then what happened is from 7.672 until 1.216, it was going backwards. So I'm going to find this displacement, and then finally the displacement from 12 back to 7.672. I need an S there. And so if I could find out how far forward it went, how far backwards it went, and then how far forwards it went, that would actually give me all of those data values. And again, this can get a little bit tough, but hopefully we've got it. And just remember, I stored some stuff in it. So when I'm looking for that 1.216, I know that 1.216, I think, is F on my calculator because it automatically stores those things. So I'm just going to put an F right here and right here. And as you recall, hopefully from class, the calculator stores the other one as letter E. So let's see what we got. So I'm going to start off with vars y vars, y1 of f minus vars y vars y1 of 0. Now this would just tell me how far forward it went. So I'm not going to need the absolute value on this one because it's automatically going to be a positive because we knew it was going forward. I'm going to help myself out and just call that A. Okay. Then I'm going to go back and I'm going to grab these last lines and I'm going to change this one right here to E. And this one right here to F. Now I should know already that this thing is going backwards. So this answer is going to give me a negative because it was going backwards. So I'm going to flip that over because of course absolute values are positive. I'm going to store that as alpha B. Okay. And last but not least, I'm going to take and grab one more piece and I'm going to take S of 12 minus S of 7.672, which was letter E. And I got 1.96805. I'm going to store that as alpha C. Again, this is what I personally like to do. So in the long run, I know that I had A was 12.097, I guess 12.098. I know alpha B was 100.904 and alpha C was 196.806. Those are all great numbers, but if I added those together, I have rounded each of them off. Even though my calculator hasn't, I chose to round them off. I'm not going to do that. I'm going to hit alpha A plus alpha B plus alpha C. So I've got all of them stored in all of their glory, and we'll see what happens. And according to this, that summation should be 309.808 meters. So, you know, my displacement was only 108 because there was an awful lot of back and forth happening and forth. This was all, it went backwards 100 and then had to go regain that time. So in fact, if you took this 309 that we had and we took off two of those B's, you'd get that 108 because we had to go back 100 and then regain the ground that we went backwards to, you know, ultimately go back forward. So it should make sense. So that's the end of the review. Hopefully you feel ready and prepared and are ready to go. All right, I'll see you back in class.